Welcome to today's webinar, where we'll be talking about accelerating validation of next-generation cloud architectures with virtual testing. So looking at the agenda, today's topic will cover networking SoC verification challenges, virtual prototyping testing using emulation, and as a case study, we'll be looking at Pensando networking SoCs. So my name is Sushil Tadikonda. I am a Vice President of Continuum Solutions in the verification group at Synopsys. And today with me is Kinjal Shah. Kinjal is a member of technical staff at Pensando, which is actually a startup, a high-flying startup, which is developing highly scalable smart NICs. Okay. But before we start the main session, let me give some logistics. During this webinar, you may submit questions by using the Ask a Question box that you see on the screen. Please note that we'll try to get to as many questions as we can at the end of today's webinar. But if you're not able to get your question today, someone will definitely get back to you after the programming is over. Okay, so now let's move on to the main topic. There has been significant growth in the overall networking industry over the past few years. This has been predominantly driven by a growth in bandwidth needs, like from new segments, new growing segments like cloud computing, 5G, AI, automotive, etc. Right? I mean, this has been a driver for significant growth in the complexity of virtual silicon also. What we notice is that the bandwidth requirements are going up. We are seeing switching speeds of around 24 terabit per second, and it is growing. And this, in turn, has led to an increase in the port count on a chip itself. We are seeing around 512 ports, and this seems to be also growing. And on top of it, the interface speeds, we used to be around 100 gig, 200. Now we have moved to 400 gig, and now I'm already seeing the 800 gig internet speeds that are showing up. More importantly, all the silicon vendors are finding new ways to differentiate themselves from each other, and programmability of silicon is one of those key differentiation elements. So overall, what we see is that the development cycles are shrinking. Okay, so the speed at which the new silicon is being put out is, with capacities almost doubling every 12 to 18 months, is unprecedented. And what we notice is that the release cycles between every generation of chip is expected to be less than 18 months. Okay, so what's happening? So what are the requirements that we see because of this growing complexity from the industry? The first one, as the chips are growing, we see a big need for high performance and big capacity emulation needs, and with robust debugging capability. The second one, as I said, the port counts are increasing. That means the number of users also trying to use this are increasing. This is led to a requirement that customers want to see highly configurable testing infrastructure so that they can test various port configurations and also be able to reach the high throughput that is needed for these kind of silicon. And also the last one, because with all these port counts and bandwidths, the scenarios, the testing scenarios are getting complex. Okay, this has led to a requirement that we need to have absolute precision control over the rates as well as on the flows, and also an ability for you to run production-worthy benchmark tests early in pre-silicon. Okay, so essentially what the customers want to see is they want a test infrastructure that is consistent between pre-silicon and post-silicon. So this is where actually we see a big push for customers from physical to virtual. Let me explain what we mean by that, right? As the port counts are growing, what we noticed is that the customers are faced with a very interesting problem. The first one, they want to move away from physical testers in pre-silicon environment, because in post-silicon, you typically use testers like the IxVerify, the Spirents of the world, and they want to bring that into pre-silicon, but they don't want to bring in the hardware. Okay, they want to see a virtual way of doing it. The second one is that the physical adapters that are typically used by most customers to connect these physical testers in pre-silicon is not at all becoming a scalable solution. Okay, as the port counts go up, it becomes very hard for you to keep increasing these wires that are connecting. So there is a big push for virtual solutions. And this is where the Synopsys virtual solution comes in. This was developed in close partnership with one of the leading network testing developers, which is Keysight IxVerify. What we have done is we have created a completely scalable solution to handle both Ethernet traffic as well as the PCIe host communication for your networking software. Okay. So what is the solution and what is the benefits that we see from this virtual tester solution that we have built? Now, one of the first and foremost important benefits that you see is in the overall market, ZeBu is the fastest emulation platform that is available today. And with need for testing so many different testing scenarios, you definitely need a fast emulator with a big capacity. Okay. The second one is that the customers have seen increased emulation efficiency using our job scheduling and cloud management. Now, bringing in the post-silicon infrastructure in pre-silicon allows the customers to do early software development and also the ability to do full chip testing and run benchmarks. Now, what we have noticed is this has led to an overall development or overall improvement, I should say that, in chip quality. Now, this kind of infrastructure allows the customers to be able to easily reproduce and debug post-silicon issues in pre-silicon. Okay, one of the big holy grail problems that we typically have as silicon developers, how do I essentially tackle my problems that I see in post-silicon and be able to quickly debug that in my pre-silicon RTL so that we can figure out solutions for it. Now, going on to talking about the solution itself, as I said, we have partnered with Keysight to bring in some of the best-in-class feature support that is available in post-silicon infrastructure out into pre-silicon. Okay. In fact, we have had to develop features in our virtual platform that are not available in our traditional other platforms that we have. Because remember, one of the things virtual allows you is the ability to do more error testing because it's all software-based, which you may find it very difficult when you're doing actually with physical testers. Just to capture on some of the key features, as I mentioned, precise traffic modeling, accurate race analysis. In fact, everything that you see, not only from rate control, but also from the statistics, bandwidth measurements, latencies, are 100% accurate with respect to your DUT. Okay. This solution provides a complete continuity, as I mentioned, between post-silicon and pre-silicon, and it's a platform that is very user-friendly and very easy to bring up in an emulation domain. Okay. Now, some of the advanced capabilities I had mentioned is in terms of the resource management and extended debug capabilities that we have, and some of the in-demand features like priority flow control, error packet generation, sequence checking of packets, and in fact, your IP error generation and statistics itself. So this is where I would like to hand off to my colleague Kinjal here so that we could look at a customer use case that has actually deployed all the feature sets that we have built in, the capabilities that we have built in, and how they've been successful. Okay, so Kinjal, I'll hand over the mic to you.
Thanks, Sushil. That's a wonderful information. So I'm Kinjal here from Pensando Systems, and I'm representing our team over here. It's not only my work, whatever we are presenting is a teamwork, and I'm just representing as one. So we use the emulation for different applications, and this is the description is all about that. So let me give you about brief history about the Pensando. So Pensando system started in 2017, and the idea was to create a solution that can have different applications. It can behave as a firewall, it can behave as a load balancer, networking applications, it can also include storage applications, and also offload engines like encryption and TLS. And all these applications are not only hardware-based, it's not only software-based, but it's all together. So as a verification, we need to make sure that pre-silicon and post-silicon works really well together. As you can see, there are a lot of different factors available. The power is a major factor, and also the latency, bandwidth, and customer use case. It may include a lot of features and integration of the different applications. Overall, it becomes a complex systems, and the idea is that with a verification and software team together, we can develop a solid system. So let me give you a brief about what we were looking when we started this project. When we started this project, there was no infrastructure available. So we were like starting from scratch. It's a brand new team. Hiring is also going on, and we have less number of resources in-house. So we laid down just the goal that what we are going to see. And the first goal was that there are lots of applications that we are trying to target. So first, we need to have a proof of concept. And then it cannot take too much time, because then if we need to re-architect, we need to upgrade the design, or we need to cut down features, we need to know as early as possible. The other challenges was that we have a simulation environment and full chip environment, subsystem environment, and it is going to work as we used to do before. But the option was that as we have minimum number of resources, so the option was that can we leverage the simulation environment and move it to a system where we can run billions of cycles. And the reason being that a lot of application and level scenarios require billions of cycles. We cannot rely on millisecond level scenario because it has to run end to end. And that brings out the next point that, okay, when we say a need performance number or bandwidth number, then we need to have a utilization ratio. So, for example, Ethernet or PCIe or memory or internal bus, then we are supposed to drive at 100% rate and different quality of service in that as per that protocol requirement. So what we did was that we came up with the plan for simulation, and then we were looking for options so that we can run on emulation. And that was our first target. The next target would be that how can we debug the forthcoming problems. So it is going to have cases where we have a functional problem which we cannot reproduce in simulation. So we have to have a tool set or debug APIs that we can check easily. But it also comes down with the trade-off. Now, how much we can check, how much we can leverage from the tool itself, and what accuracy it brings down to. So simulation model, we can review, we can look at the waveform, we can check, but on emulation, how are we going to correlate stuff? So those are the challenges, and then we contacted ZeBu, and then they come up with the solutions that they already have these transactors available. They have this, as Sushil mentioned, they already have IxVerify already integrated. So packet generator, virtual packet generator is already available, and PCI transistor is available, Ethernet transistor is available, and internal bus are also available. Then that was a quick help in creating peripheral transactors. It comes down to integration, but then they also have a tool available. So overall, that was a benefactor for all of us. Now, when we started, I'm just giving you now next, let's see how our use cases are. So here in this box, I'm showing you A, B, C, D as a subchip block. And then these blocks they are all having their own functionality. Now, on top of it, we use ZeBu solution, and they provide us the synthesis tools and entire tool chain with transactors available. IxVerify is also connected, and it will work as a virtual Ethernet packet generator. And the networking application over here is developed by us. So the idea that we came up was that on the Ethernet side, we already have IxVerify available. And then on PCIe side, it is a user application that we need to develop. Now, the first question was that if we can create a user application to use IxVerify itself to generate a packet and receive a packet, then we can leverage IxVerify features to send traffic from PCIe itself. Once we do that, then PCIe to Ethernet and Ethernet to PCIe traffic can run as a end-to-end traffic. But the problem was that that is not that easy as well. There is a lot of work in the backend. So this user application needs to be aware of the DUT itself. It needs to be aware of Ethernet packet. It needs to be code needs to go through a lot of processing before it can hand off to DUT. And then when we receive packet from DUT, then we do the reverse thing that we need to declassify, and then we need to send back to IxVerify. And each of these processes, we need to add checkers, and we also need to add more transform of packets. As TLP data, PCIe TLP data is different than Ethernet data, there is a lot of packet transformation in place. But ZeBu also has capability to, on a ZeBu solution, there is a capability to run multiple images in parallel. So in case if we are able to stub out a feature, like here I have shown as a stub out C and stub out D, then the ZeBu utilization will be 50%. What it means is that for the given setup, now instead of running full SoC, we can run two sets of half SoC. Just giving an example. What it brings down to is that we can run, two people can run parallelly, and that can accelerate overall development. So for example, I can start debugging PCI side, and other team member can start working on the Ethernet side. And then once it is ready, we can go back to a full chip where we only utilize the ZeBu card, and then that becomes a good solution. So we can debug this thing in parallel. But for doing this, in order to achieve this, we need to have a network application. So whosoever is transforming this package, and whosoever is checking this package and doing all the in-order checks, they need to be also aware of these stub modes. Once we are able to control that, everything is good, and then ZeBu does support this feature, and we use this very efficiently. It also comes down to now what rate this ZeBu run, right? So there are two modes within ZeBu, and then there is one called free running mode, and the second one is the clock control mode. If it is a free running mode, then we are getting like 400 cycles per second. Now, just to give you perspective, in simulation, when we run full SoC, then we are getting like 100 cycles per second. Versus here in the free running mode, we are getting 400,000 cycles per second. there is a one catch there. So catch is that we are running a user application code attached to a PCI transactor. So there are cases where we want to utilize PCI 100%. And what does that mean? That means that the application which is running over there may take substantial amount of time. So for that amount of time, if emulation is running, then those will become idle cycles. Now, to eliminate the idle cycles, we need to stop emulation because user is processing the data. So there is a clock control mode. In the clock control mode, you stop the emulation, you let the user code finish, and then you trigger emulation to go forward. So it is very accurate, it is very efficient also, but it gives you 50,000 cycles per second. And remember, with respect to simulation, this is far faster, but with respect to freewheeling mode, it is slower. In return, you are getting a user application which is running completely in sync with emulation. So the performance number and PCI utilization is 100% accurate. So when we run post-silicon, this number does match, and that is important over here. So in order to send traffic, we use a virtual tester, and on the PCIe side, we create a producer-consumer queues. In these queues, whenever we receive packet from IxVerify, we first classify, because there may be multiple producer-consumer queues, so we do classify them. Then we hand over to DUT, and on the then it becomes a DUT traffic. Then that can come back to Ethernet, and also it can come back to PCIe depending upon how we program the chip. It is highly programmable, so as per programming, it can behave differently. Once it comes back to PCIe, then you do reverse. You do first check what producer-consumer queue it came up. It is correctly came up on that or not. So you apply checker there. Once checker pass, then you do some measurement like latency, bandwidth, etc., and then you hand it over to IxVerify. Now IxVerify does represent latency, in-order check, and other Ethernet packet level checks, and so that is already taken care by IxVerify. The Ethernet side, when packet goes to Ethernet, they also have a hooks to check in between if you intend to do. So the Ethernet transmitter already have callbacks available. Before it goes to IxVerify, you get chance to inspect the packet to apply your own checker. So our checker works from MAC to PCIe, and MAC to MAC and PCIe to PCIe also. We also have an internal bus like on-chip bus, and packet can also appear over there, and we have also hooked up checker over there. So each packet and each traffic on these buses go through this analysis, and once it is passed, then only it is reported good. So now let's come back to accuracy, because I mentioned about accuracy. So it's important to go back to how accurate and how easy to use ZeBu. We found a recent situation, and it is important to note down, is that we found a post-silicon software debug that we were trying best to figure out on without doing any simulation, and it was taking time. So then we came down to rescue, we came down to ZeBu, and they rescued that. The way they work is that we need to create the same scenario on ZeBu, and ZeBu will report if there is a mismatch in programming or anything like that. So we tried over there. First one day we debugged, but then we found a programming issue, and then next day we hit the exact same condition as we were debugging on software. Once we found and we hit the condition, we easily get a waveform. The designer looked at it, we found a misprogramming. It was a simple thing, but over the complex chips, it is very difficult to pinpoint where the exact problem is, and ZeBu really helped in this. So post-silicon, condition we were able to reproduce over here. We also have some performance numbers and bandwidth measurement already available pre-silicon. Now, when we run performance numbers, this is a networking solution. So we need to go through the packet sweeps, traffic rate, lots of latency variations, the credit. So per queue, per cost, there is a number of packet cells available. So we have different variation in each of these setup. There are a lot of factors depending upon how PCIe credits are working and internal bus is working. So number of iterations, and if you just apply the permutation, is a lot more. And a lot of cases requires millions of cycles to go through the condition to say this is going to work fine. So on simulation, million cycle may not be possible, but you can go to like sub-millisecond level and then you can fine tune. But over here, it's way easy to just run these cycles. We also went over lots of cases where we had to debug issues. Some are functional, some are non-functional. So overall, it worked out really well. We got easily waveform, we debug, and then we rerun them, and then cycle becomes really faster. The synthesis flow is also automated over here. So overnight, we get a new design synthesized, and if it is not full SoC, it is sub SoC, then it is even faster. So that also helps us a lot. Initially we had all have a doubt that, okay, how accurate is this model? How it is different than simulation? The transactor may not be as accurate as we are thinking. So we also undergone the correlating ZeBu transactors with our simulation transactors. And post-silicon also, we saw the same result as we were seeing on ZeBu, using very sub percentage level accuracy. So it's very, very highly accurate, and we see a lot less variance post-silicon. The ZeBu also, because our infrastructure was not available at beginning of the project, so by using this platform, we also realized that lots of debug API and performance APIs can be developed in pre-silicon, and we use them along with the ZeBu, which were very useful post-silicon. And when we got in the lab, our libraries were already available, and then we started debugging stuff on day 0. Now, to debug any ZeBu conditions, there are solutions that we develop internally, and the ZeBu tool itself has lots of capability to inspect that. So first condition I will be the trigger point. So if you exactly know that if A signal A, comma B, comma C happens, then you just stop the emulation, and then you want to inspect the stuff. So it is a conditional trigger point. That's very useful when you know a fatal interrupt should not happen, or a link goes down when we send this particular erroneous packet. So those are where the good use point exactly if you want to reproduce and recapture the waveform. But that doesn't work when we run billions of cycles of simulation because at that time you don't know exact fail conditions, and if it fails after billion cycle, there is no point of rerunning them. So at that time, the snapshot and replay comes to rescue. So snapshot and replay is taking a snapshot at a periodic interval, let's say every 30 minutes. So every 30 minutes, it will keep taking a snapshot. When it takes the snapshot, it captures the current state, and it also records the peripheral inputs. By doing that, the advantage is that you may run 1 or 2 billion cycles, But then let's say you find that this error condition is already triggered, then you can go back every half hour to find the exact window which you need to get away from. Now, when you know the window, you just replay that part and not entire billion cycle. So that gives us a lot of advantage in replaying and running more number of cycles, because we know that whenever anything fails, we can definitely go back and find our error window. Obviously, the full waveform options is always there. So if this is the slowest possible, but it definitely works. So if none of your debug internally developed tool or any of the other ZeBu debug works, then full waveform definitely comes to rescue. We also use translator logging. This indicates that for the ZeBu specific purpose, we can inject some of the code inside the design, which will send from DUT to outside file system. This is continuously sending traffic from DUT to file system whenever it is enabled. Once you enable, it will start sending that data. We use this one for our performance analysis. If we want to make sure that what is current condition of the chip or current condition of the peripheral, then transactor logging is very helpful, because it is exactly like you are recording exactly what transactor is doing or what exact internal design is doing. And we use transactor logging whenever we need it. Along with that, we also develop our internal tools, and as I mentioned, that was useful post-silicon also, and we keep enhancing this. This is for application specific, and we keep developing them. The internal tool, we develop some of the tools where ZeBu specific, wherever they dump the waveform, we post-process the waveforms. When we post-process a waveform, then some of the sanity checks and performance and latency numbers are already extracted by our internal tools. And that was very useful, because every designer need to know what are these parameters upfront, so that a lot of issues are straightened out right there. So overall, our experience with ZeBu was great, and they bring a lot of value to our solution. And we feel very confident pre-silicon and also post-silicon. So I think that's with that, I would like to hand it over back to Sushil.
Thank you, Kinjal. That was a very informative presentation that you gave, where you highlighted all the challenges that you guys face and how you've been successfully using ZeBu virtual network solution, right, as a validation platform. So just to summarize, our pre-silicon, the Synopsys pre-silicon network validation solution has enabled a complete end-to-end validation of networking applications in a very, very short time. Okay, so what we have provided is a complete infrastructure that allows users to create different traffic test scenarios, debug any failures that you see, and also to generate 100% accurate results, which can be correlated to post-silicon also. So what we have is, we have many successful and significant success stories with some of the major silicon developers who have used this solution. To highlight, in fact, one of our big customers who makes the high-end switching silicon, they were able to ship their latest switching silicon within 1 day of it being in the lab. Okay, I mean, this is unprecedented. Usually it takes months before you typically do that, but what it shows is the utter confidence in the infrastructure solution that we have built. On top of it, ours is a solution group that is very networking savvy, and we speak the language of the customer, which has helped us in our engagements with it, because we understand the customer problems, what they're facing, And we are also able to create custom solutions for the customers as needed. And also, as Kinjal mentioned, accuracy of results is a prime requirement, and they have shown that they're able to correlate all their pre-silicon data that they've computed to post-silicon. And we have seen this across all the customers. So essentially, bottom line is what we have is a proven and scalable pre-silicon network validation solution. Okay? And with that, we will conclude the main topic itself. Now we can go for Q&A. And as I mentioned before, please send the questions by using the Ask a Question box. Okay, let me see. I can already see one question coming up. Kinjal, this would be for you. Can you give an example of how you verified networking designs in the past and what issues you ran into?
Oh, yeah. Yeah, it's an excellent question. So we did, in the networking design, we always try to do simulation first, just like regular verification. And the issue over there is that in the networking chips, number of ports are increasing, and a lot of combinations are also there. For example, 10 gig, 40 gig, 50 gig, 100 gig, 25 gig. And each port can be configured different ways. On top of it, there are a lot of queues, 8 queues per port, and you can enable selectively on that. So combinations are many. So we end up having lots of test cases, and then at the end, it takes up lots of simulation time. So that is always a challenge, right? So it is always time consuming. When you say this is a final and pre-silicon is ending, you always have to read a lot of test cases. Performance numbers are a lot of assumption level. So because you always take a window, right? Like millisecond, 2 millisecond window. So that's always the case. So recently we have seen that emulation has become a norm, and I second that, and it's really good because you get millions of cycles, and you can try a lot of combinations with a period of time. And with our IxVerify integration, it becomes even easier because we already have in the lab the physical IXIA, and we already have scripts available, and IxVerify uses the same scripts. So we use the same pre-silicon script to post-silicon, and the same scenario across the chips are also possible. So yeah, previously that was not the case, and now it's possible. So across the chips, across the generations, you can use the same test cases. So benchmark cases, everything is very easy now. That's possible. Oh. Thank you. That was a good question.
Okay. So essentially what you're saying is end-to-end verification is a must, and you need to have the ability to create those kind of scenarios for end-to-end testing and get accurate.
Yeah.
Okay.
Exactly. And also software integration. Yeah. Because previously to get a software integrated pre-silicon was like a dream, right? Now with this, we are able to, like even before tape out, we are able to integrate our software, and we are able to run millions of cycles. It's not like simulation anymore, right? So it's very helpful.
Absolutely, I agree with that. Kinjal, I think we have time for one more question, and I see another one popping up here.
Okay.
This is a sequel to the previous question itself, so it blends very nicely with that. What are the biggest risks you see when you don't do full SoC emulation for networking designs?
Oh, yeah. So if you don't do that, then I think this brings up the SoC simulation brings a lot of values. For example, performance numbers only matter when you run longer. We have seen cases where after seconds, the performance number degrades. The first it works great, like first few milliseconds for seconds works great, and periodically it goes down. And and back pressure from each queue, the PFC, the PCIe credits, those things work at the seconds level, right? Millisecond, sub-millisecond, and seconds level. So it does matter. If you take emulation, you are able to, you are very confident silicon level. And again, as I said in the previous question also, the software integration, a lot of times we think that software will use this config, it will use this mode to set up set up a condition. But when in reality, when they try to do that, it may not work as expected. So if you do SoC emulation, you are going to find a lot of issues. And it's not hardware specific, but mainly it's the integration level and performance point of view also. You run billions of cycles, so it gives you lots of confidence.
Okay. I mean, essentially what you're saying is for networking designs, the chip needs to come to a complete warmed up state, both with respect to FIFOs, the traffic manager buffers, everything, for you to really see some of the interesting scenarios. Okay. And for this, you definitely need a complete software and hardware infrastructure so that you can actually stress the chip out to bring out some of the tough bugs that you may have to find.
Yeah, exactly. If you know exactly where the bug is, you are going to simulate in millisecond, right? So if you simulate millisecond thing, then you will find it. But how you find it millisecond, what condition you find, right? That's the problem. So emulation runs for like this many cycles, right? So it becomes really easy to pinpoint exact failure, and that's pretty easy.
Okay. Yeah. All right.
Good question.
We are
Thank you.
pressed with time right now, Kinjal. So thank you very much. This has been a great session, very informative, and I hope the users find it very useful. And as I mentioned, any questions that you have, please send it to us, and we'll be happy to respond back. Thank you very much.
Thanks, Sushil. Bye.
Bye.